Get into this, we're going to be talking about small-scale solar systems here. You've heard in the early presentation some of the reasoning behind this stuff, and we'll reiterate some of that. But this is really, this permitting process is really intended to put together a format so that jurisdictions and contractors can get on the same page. Ideally, when we're talking about residential projects, we're looking to pull a single permit. Now that permit may have multiple aspects to it depending on how our jurisdiction operates, but one of the things that we're trying to work with and deal with is we certainly over the years I've pretty much heard everything in this particular field, but we may have jurisdictions that want to pull a structural permit, an electrical permit, and you know, there may be a variety of things that they want to do in that process, and because of the requirements of their community, those things can take a lot of time, and a lot of people have to touch them, and so part of this process is how do we get these down to the point where possibly a single person could be empowered with the approval of a permit package and address the concerns of the fire service, the planning folks, electrical, structural, all those. So it's likely that most residential systems are going to comply with that. What's it telling me? But you're still sharing posts. Is that okay? A little. Okay. This is designed for residential type construction. As many of you know, a lot of our small commercial construction is converted residential, so the structures may be identical to a residential structure, and so if so, these materials certainly comply and relate to those things. And as we get into larger systems and more complex buildings and things like that, that's where this simplified processes may not hold up in their entirety, and so that's why we're really focused on those smaller size systems. And quite frankly, the whole idea of simplifying is related. The smaller the system, the more you have to simplify, because the permitting process, all the things that go along with making a project happen, those costs and those issues and efforts are far more magnified in a small project than they are in a larger project. When we get into a 50, 100 kilowatt rooftop project for a commercial building, or I've done a 5 megawatt rooftop project, you know, the engineering that goes into that and all is an obvious part of the whole process, and we're not trying. I know there's been communities trying to come up with simplified guidelines for 500 kilowatt rooftop systems, and there's just, in my opinion, there's just no point. There's, you know, we can talk about some of the processes that you want to make sure happen in that, but the reality is we're going to have structural engineers, we're going to have electrical engineers involved in the process, and it will work its way through. But we certainly don't want to take those same processes and go down to a 5 kilowatt system on a residential rooftop, because that project will not happen. Just as a little aside, you know, when I got started in this 30 years ago, it was really common for a utility company to say, we need a check for $30,000 to study whether or not you should do a 3 kilowatt system on this house, because we need a lot of information about that. And maybe it was just because that was their standard process for any kind of generator that came on their system, which was often the case, or maybe it was because they were purposely trying to make it not happen. But the reality is that, you know, obviously, if somebody's got to pay $30,000 just for an engineering study, that's a no-go from the get-go on the utility side. And so certainly other things like that can affect us on the permitting side as well. We've seen permitting costs all over the map, and we're not going to get a lot into detail about how much a permit should cost, but in general, permits should cost what the jurisdiction actually puts out in the process. And so with the idea that initially community may spend more time on these things as they become familiar with these technologies, but at some point in the process, these permits should really be no different than an HVAC permit, things like that that are done every single day, routinely, for pretty reasonable prices. So that's where we're going. In fact, over the years, I've certainly used HVAC projects as a very good comparison as far as the level of project, the level of effort involved, the level of engineering that's necessary, things like that, to a residential PV system. So it's the idea is that this would comply with most residential systems, as I said. Simple criteria that address the requirements of building, electrical, and fire codes. So we're going to have an eligibility list, and that's going to create what I would call a box that's going to contain what would be considered a simple system or simplified system. And that's a really important concept, because it turns out that a lot of folks want to do a lot of different things when it comes to solar. And so they may want to do things that are maybe outside of a simplified process, and that's great. We have a construction process for every community, but we're not intending that we would expedite every single solar project, because the reality is a lot of folks want to do some really interesting things, and that would fall outside of the process as far as from a simplified process. But the reality is that the vast majority of systems that are going in are very simple, grid connected systems without battery backup, things like that. We will talk about batteries today. They certainly will become a part of the future of PV systems in a bigger way. They always have been a part of PV systems over the years, and certainly the systems I've worked with over the years, many of them have had batteries in them. A lot of folks are discovering batteries for the first time. It's nothing new, but there are some new standards. There's certainly some new technologies like lithium-ion that have really developed well over the last several years, and we'll talk about that. But as it stands right now, we're putting those types of systems into not in a real simplified process from the standpoint of installing many solar projects. Certainly in the near term in this region, not many residential systems will have batteries in. Only a small percentage will. Over the next several years, we'll certainly see those numbers grow, and there's efforts underway to develop simplified processes for battery systems as well. We're going to talk a lot about structural review this morning, and basically check boxes to determine whether the structural meets the requirements for the simplified process. And then we'll talk about the electrical review, which quite frankly has become a lot easier over the last few years. The products are pretty straightforward, and we probably have more emphasis now on the structural side than we did on the electrical side. Some of the reasoning behind that is that the electrical code, Article 690, which is solar photovoltaic systems, has been in the electrical code since 1984. That's a really long time. Now, there was very little activity related to the electrical code until probably around 1997, 98. And most of that started in California and then started working its way across the country. But we do have maybe 20 years of experience of the wide-scale use of the electrical code related to PV systems. In stark contrast would be the building codes and the fire code. The residential code, building code, international building code, and international fire code, and NFPA 1. I think Maryland's an NFPA 1 state, is that right? Then NFPA 1 and IFC say almost exactly the same thing related to PV, so it's really no difference. But these codes didn't see anything related to solar PV until 2012. Big difference in where these codes are related to these systems. And in any kind of code where it's fairly new, there's usually a fair amount of movement in the code in the first couple of code cycles, which we certainly have seen: the 2012 code, 2015 code, and 2018 code, which has recently been finalized and will be published in the next. Actually, I guess it's been published now. They're in the printed version, and we should be able to get the PDF fairly soon for the iCodes. But again, these things are in flux, and the pendulum has moved around a little bit over those last couple of code cycles, and we're going to talk a little bit about the building code. All these codes are based upon ASCE 7, which is the structural guidelines for buildings. Again, we're focusing on buildings. Recently, I saw a community that was trying to apply requirements for buildings to a ground-mounted PV system, and it's like, it's not a building. Okay, well, it is a built thing, but it's not a building. And so they were trying to, well, it's type U unsprinklered building. It's like, no, it's a structure. It's like a fence. Okay, a fence is a type U structure, but that's not something we put sprinklers on or not sprinklers on or things like that. So it's confusing to a lot of jurisdictions as far as, okay, what part of the code do I actually apply? What makes sense? How do I apply the rules? What's safe? So as we get into required information for permits, obviously most communities have some type of an application process. So that application process is gathering basic information about the scope of the project, location, who's doing the work, all that kind of stuff is in that part of it, and that's universal. That's going to be information that we need on any project. The next part of it is going to be a site plan showing where the major components are on the property, and we're going to show you some examples of that. Because there's some detail that we need when we do rooftop systems. There's some information and detail we need that has to do with the structural side of things. Also, that structural information feeds directly into the planning side of things. And so there's several people here that are kind of on the planning side. And so one of the things that was mentioned in the opening presentation is one of the areas in SolSmart is dealing with planning and zoning and things like that. And it turns out that when you go through the simplified permitting process, because of the structural constraints that we put on these things, those structural constraints actually feed directly into the planning side of things. So that, for instance, if you want to do a simplified PV system, the array is going to be within the plan view of the roof. It's going to be away from the edges of the roof because of wind loading issues. It's going to be parallel to the roof or largely parallel to the roof. It'll certainly look parallel to the roof because it's going to have to be within 10 inches of the roof surface and things like that. So we have all these structural rules that we put into play that actually play directly into the aesthetics of the project. We'll probably see some examples of some horrible examples of really poor aesthetics that are certainly a concern to any community, and they're a concern to me as well. Basically, having been in this field for so long, we're up to well over 1 million systems. We'll probably be up to 2 to 4 million systems in the next 5 years, and we don't get to millions of systems if they look bad. And so my perspective on things is I'd much rather see smaller systems that fit on a building, look like they belong there, than people trying to use the structure of their building to create something that looks like it's from the movie Up or something, where it's got things hanging off the side of it or whatever. Just craziness. So arrays are in compliance with fire setbacks and don't need a fire service review. And so as we get into some of these issues, there may be a need to have a memorandum of understanding with the fire service, with the planning department, things like that, so that if the project meets these certain guidelines, they don't have to touch it. Okay, it's an automatic compliance. They give that information This is done all the time with the fire service. Fire service rarely ever touches a residential project. It doesn't mean that there is no fire implications to residential projects at all. It just means that the fire-related issues are enforced by the building department on behalf of the fire service. And this is done all the time. And so there may need to be specific permissions involved in order to do that. The electrical side of the house, we got several electrical folks in the room. And this is the side that I've certainly had a lot more to do with over the years. And we're going to lay out the configuration, wiring, the equipment, AC connection to the building. We're going to use a standard plan, a couple of standard plans in order to pull that off. And then lastly, specification sheets, installation manuals related to this equipment. One of the reasons that we like to talk about electronic submittals is that there's a lot of information out there that could be really difficult or cumbersome to print out. So some communities might require 3 to 5 copies of a permit package. Installation manual for an inverter might be 300 pages long. In that installation manual, there's about 5 pages that actually have to do with physically installing it. The rest of it's related to things like programming the interface for monitoring and things like that, things that have absolutely nothing to do with the local jurisdiction or safety. And so there's a couple of ways of doing that. If it's required to be in a printed format, then I would recommend only printing those parts of the manuals that actually relate to the installation. And if you don't require printing, then certainly supplying the whole document is not the worst thing in the world. Although the other thing is, I don't want to have to wade through these documents to find the stuff about installation. So it'd be nice if somebody actually kind of curtailed that for me to the 5 pages that I really wanted to see and enforce. So our major components, we have PV modules. That's the things that make the electricity. DC converters are a common part of PV systems nowadays that might plug into every module. We have inverters. We have microinverters. Lots of different ways of doing this stuff. And then the mounting systems, as I said, the structural side of this stuff has become a much bigger deal over the last several years. Not because we've had a lot of structural failures, because we really haven't, but more because the structural community has become a lot more aware of what we're doing. And so they have a lot more questions. And so they have a lot of interest in making sure things are done properly from a structural point of view. We certainly don't want to see structural failures. We don't want to have panels flying off of roofs and things like that. And so the mounting systems and what is related to those things. Anybody in the room structural engineers, structural folks? Okay. Not that many, but we're going to go in and we're going to do a little training on structural issues. For those of you who are not familiar, you're going to learn something about structural. Coming out of that, certainly there are folks in your communities that are heavily involved in the structural aspects of these systems and that are going to have a lot of questions. And we've put together a 60-page commentary on our structural notes, and so that it basically we want to overwhelm people with information when it comes to that kind of thing, because those folks have a lot of questions, and we want to make sure they understand that, yes, in fact, this is not voodoo. We are connecting it to the building and things like that. So some of this stuff was already said. Reiterate a little bit of it. We're consolidating the structural, electrical, and fire review into one package. And the idea, again, for small-scale residential, eliminating the need for detailed engineering studies and avoids necessary delays if it meets the requirements. Obviously, we can have houses that don't meet the requirements and that need specific engineering related to them. And so we're not saying that we're going to be able to get away with this and do it this way all the time, because the structure may not meet the requirements. And we're not circumventing engineering processes. The idea is that we're showing clear compliance with electrical and building codes in the process. And so that's really the key at the end of the day. We're also going to talk about inspection today. So we have several inspectors in the room, and so that'll probably be the part that's of most interest to you. And so having a concise inspection checklist, very critical thing. There's been a lot of folks come up with inspection checklists over the years, and the vast majority of those inspection checklists are far too detailed. They have far too much information in them. They're interesting as a document of all the things that you could consider in a PV system, but I find them to be not very helpful in the field. And so when we get out in the field, for a residential inspection, what's a typical time frame a field inspector might have to review a project? 15 minutes. Okay, that's a very common number throughout the United States. You got 15 minutes because you might have, I've heard inspectors doing up to 20, 25 inspections in a day. Now, they have to be pretty close to one another just because the physical speed of getting from one to the next, but you know, 8 to 15 is not an uncommon number for a field inspector, and we're looking for safety violations. We're looking for things that could be a problem. We're looking for basic compliance. We're looking to make sure that what was permitted is actually what's been installed, and it's been installed properly. But we have about 15 minutes in that process to make that determination. And if there's problems, then obviously it's going to create difficulties in passing the system. And so there may have to be a need for multiple inspections if the contractor is not ready and hasn't done everything they should in the process. However, if everything's in order and everything's been done properly, according to the code and the signs are in place and everything like that, 15 minutes should be plenty to get that done and approved. So that brings in, there's a whole bunch of technology being worked on in that whole area, which is certainly well beyond solar, but it's being worked on by a lot of solar companies and companies that work with solar projects, and that is you know, coming up with GPS locations of where inspectors are when they get hung up on something, just to allowing people to know where people are at, what their time schedules are, what delays they might have occurred, or maybe they've picked up speed because maybe they get to a site and the contractor's clearly not ready. And so it's like, hey, I'm not going to waste my time here. I've got more inspections to do. So now the timetable might move up. So all those things, there's a lot of technology going into that. And so, you know, I expect over the next several years, just like things like Uber and stuff that have changed our lives that are, you know, 5 years ago were inconceivable. We're going to be looking at our phones, knowing exactly when an inspector is going to show up. And those are a lot of challenges in the construction world. Is, you know, the inspector's busy, they've got a lot going on, and they've got, you know, but when are they going to get here? Well, you know, am I going to stand around all day long? A lot of solar projects, especially residential, you know, a person who's overseeing those projects might have 4 or 5 projects that are being inspected in a given time period, and that can be a big time sink trying to coordinate with field inspections and things like that. Once the system has been inspected, different utilities, we've got some utility folks here, so it's nice to be able to maybe bounce some things off of them as far as notifications and things like that. So normal construction, if there's somebody doing work on a service upgrade or something like that, there's usually some type of notification to the utility that the project's ready. That notification may come from the contractor, it may come from the city, and so it depends on how the process is set up and how convenient that whole process is. Normally, I'd say that most commonly in the United States, it's the contractor that notifies the utility that a final inspection has been approved. And so that being said, there's certainly other communities that also directly notify the utility company in those cases. And so some of that, getting those things worked out so that the utility knows that it's okay to schedule installing a meter or whatever they have to do for their program concerns. So, any questions about this so far? Kind of basic general stuff. Okay. So let's talk a little bit about the box that I'll call what I call the box. First of all, we're going to say, well, it's not going to be any larger than 15.36 kilowatts. Why did I come up with that number? We'll see in just a minute where that number comes from. I like to use weird numbers because it gets people to think, because in general, I don't like using numbers for cutoffs because it's related to how difficult the system is relative, and it really is relative to the project. A larger home with a larger service can be quite easy to do an installation at, and a small home can be challenging. And so understanding what the issues are is really more important, and kind of putting things relative in the box to how difficult the project is rather than a size. But okay, if we want a size, we'll put an upper bound on it of roughly 15 kilowatts. That's the largest system you could install on the load side of a 400 amp service. Okay, fine. We're talking about, again, 1 and 2 family rooftops, structures, or structures of the same construction. As I mentioned, a lot of our commercial construction may be originally a 1 or 2 family home and was converted. Then string inverters, DC converters and microinverters. Those are the three major types of systems we see installed in the field today. We have this eligibility checklist. So the 15.36 has to do with the fact that the code has limitations on the size of a circuit breaker we can put on the load side of a service. And 80 amps would be 120% of a 400 amp service. And so that's where that comes from. But that's an awfully large system. Very few rooftops, unless it's an extremely large house, could handle a 15 kilowatt system. A nice rule of thumb is about 10 watts per square foot, or 100 square foot per kilowatt. So that'd be 1,500 square feet of rooftop, which would be equivalent to probably about a 4,000 square foot house on one level. There's not that many 4,000 square foot houses in your communities on one level, except where rich people live. And so we're not saying that that's a common thing. We're just saying that that's a if you wanted to put an upper bound on something, that would be an upper bound. But the upper bound really has more to do with the size of the service, so that it's really an 80 amp breaker in a 400 amp service. And so if you have a 200 amp service, then you're talking typically about a 40 amp breaker in a 200 amp service, and down the road we go. And so we have a table that shows you, okay, here's the size of your panel versus the size of your circuit breaker. Depending on that configuration and the ratios between those two things, we can have systems of sizes, all throughout that range.
Good question for you.
Sure.
You can talk about the Tesla solar panel roofs at all?
Tesla solar panel roofs. I think we just did. Yeah, so it's always helpful to talk about things that are in the news, and clearly Tesla and Elon Musk has been very effective in getting ideas and concepts in front of people, and been rather successful with many of his business ventures. And so one of his latest business ventures is his rooftop. He's recently taken over Solar City, company with the green trucks, and certainly is using that as an avenue for one of his ideas, which is this particular rooftop project. The concept that he's working with is nothing new. It's been around for a very long time. In fact, what we call building integrated PV there were probably 10 manufacturers of building integrated PV in 1981. 1981. All right. Companies, little companies like General Electric, were building integrated products in 1981. None of those products went anywhere. But and if you were to talk to somebody in 1981 and tell them that in 2017 we'd be installing framed modules on rooftops, they'd laugh in your face and say that's the most preposterous, ridiculous thing I've ever heard of in my life. We've been doing that for years at that point. So the concept's nothing new. It's certainly been an expected concept that would become ubiquitous in the residential market, and it just hasn't happened, quite frankly, for a lot of reasons, and not just because it's a very challenging thing to do. The challenge is not insignificant. I've been involved with many different products in the building integrated world over the years, and most of them are abysmal failures. This is the latest and maybe the most promising so far, maybe. But if I were a betting person, I wouldn't put a lot of money behind that personally, just because I've seen too many things come and go. But I'm a very cynical person, and so I've been cynical about a lot of things that have actually panned out, and so yeah, it's a huge challenge. It really is, and he's got a tiger by the tail there, but he sends stuff to outer space, so you know, okay, fine. I have seen lots of companies come and go over the years because they've solved a major issue in the internet. You know, I live out near Silicon Valley, so we got a lot of really bright people doing all kinds of amazing, crazy things and solving the world's problems. And then they become very altruistic and say, well, I got a ton of money now, so I'm going to solve solar. It's like, and you guys have been working in solar for 20, 30 years, you're idiots. You're just a bunch of morons, and clearly you don't have the benefit of my understanding, and so I'm going to come in, I'm going to fix it for you. And those guys usually dump a couple $100 million and they're gone. And so I'm thankful for their $100 millions. They employ a lot of my friends, and then they're gone. But we'll see. And so Tesla, obviously, they make the car, which has been very successful, which has made them successful in the battery world, because that's really the big play with the car is the battery. And so there's a lot of promise of what they might be able to do with that battery in residential and in commercial. Personally, what I see, we're taking a little rabbit trail here, sorry, but hopefully this is interesting. Is this kind of interesting? Okay, good. My perspective is a car like a Tesla, we're talking about having a battery that's anywhere between 50 and 120 kilowatt hours, which may not mean a lot to you, but that's a lot of battery, okay, to run a car. A typical residential battery system that we're talking about as far as energy storage in a house is between 5 and 20 kilowatt hours. Much smaller that we'd actually put in a house, and we'd use it for backup purposes and maybe for some arbitrage with the grid or whatever, I don't know. But the idea is the power goes out, you still got lights and things like that. Those are fairly small batteries. We're driving around a 100 kilowatt hour battery. So what makes total sense to me and will happen in the not too distant future, and it's been talked about for years, is what we call vehicle to grid. And that's where you actually plug your electric vehicle into your house, but it's a two-way street. So you obviously want transportation, and that's your primary use of that vehicle. But if you were to have an outage, 5 or 10 kilowatt hours of the storage capability of that car would be insignificant to its range. Really would be insignificant to its range. And so, and it'd be a whole lot cheaper, and we'd amortize it through the car rather than trying to buy a separate battery and pay for that separately, and that battery just sits as a boat anchor in the corner until there's an outage. So lots of really cool stuff coming down the road, and all those things are being talked about, and the wheels are turning. So when we get into things like storage that's stationary, it's got to have a lot of value. And right now, the value that we have in stationary energy storage is pretty small. Utilities got to give us a lot of benefit for having that energy storage, which means that there's got to be a big differential between maybe on-grid and off-grid rates that would cause us to want to store energy in a battery and then use it when we have high energy costs, things like that. That's one of the reasons we use the arbitrage of a battery. Also, if the utility service is very poor in an area, then battery storage becomes interesting. Well, utility power is generally very good in urban and suburban environments just because of the interconnected relation of our grid. But then, of course, what you're hearing nowadays, and we'll finish this little rabbit trail, is resiliency, right? So that's kind of the latest watchword, which is things like backup power and what happens if all hell breaks loose. Well, we've been seeing hell break loose in quite a few communities in the last couple of months, and so having backup storage and things like that could be really important.
About that. Those who know big energy tax and storage tax credit that will go into effect in January, so that, so before that.
Yeah, great. And that's one of these, we'll talk about some permitting of those types of systems. It's very early on for a lot of those products. In fact, you know, back, anybody remember Y2K? I know so few people weren't born, but Y2K. Sorry. This little event happened a few years ago, and back in 1999, 100% of all PV systems had batteries. 100%. Okay, and it was done because of concerns about Y2K and about what's resiliency and all this kind of stuff. We didn't call it resiliency back then. We talked about, I don't know, the world coming to an end or whatever, you know. And there were guns involved, but that's another story. So anyway, but the reality is the vast majority of systems had batteries in them, and we had some pretty nice systems. They were pretty well built, pretty well organized, laid out, and so it's kind of funny. So the permitting process did a lot of talking with jurisdictions about how do you permit batteries back in 1998, 1999. A lot of questions about that. And so we'll talk about some of those things when we get into that section. And but the batteries that we have today are just now really getting back to where we were 20-something or 18 years ago, because we had far more batteries in residences back then than we have today. And so now we have some really interesting markets that have blossomed in Hawaii. The reason the Hawaii market has taken off is because the utility is saying we're not allowing you to export power to our grid. You got this big PV system that you're not using all day long, say when you're out at work, and so that, what do you do with that extra power? Well, now you put it in a battery rather than send it off to the grid if the utility won't accept that power. And now you're like, well, why do I need a utility? Because now I've got enough energy storage that I might be able to just unplug from the grid. That creates a whole bunch of other interesting issues. But anyway, so that's a little bit about what's going on in this world, and hopefully that's interesting as we move on to our next section here. So we're going to talk about structural the next bit here. In fact, just to stay on track here, I'm going to pull up our agenda, or at least the agenda that I have. I think it's here. Just so we know where we're going here. So around 10:45, we're going to take a break, and then after that, we'll take us up through lunch. So that's as much for my benefit as yours. And let's Back over to here. Okay. So we're going to we'll go through these structural guidelines, kind of introduce you to this whole concept. Given the fact that you're not structural people in general, I don't want to bore you with this stuff, other than to let you know that it's very comprehensive. And so for folks in your office that really care about this stuff, we want to make sure that they understand that it's been well addressed. And we're certainly available to answer questions as we get into this stuff. So this is a checklist type of a thing where we go, okay, you got to check off all these square boxes you have to check off. If it's a slanted box, then it's an option for compliance underneath that. And so we're going to talk about some of the general requirements, some of the roofing requirements, and then get into two different types of structural attachment that we do in residential construction, and that is member attached and sheathing attached. Okay, this is the first guideline that is attempted to address on a national level both member attached systems and sheathing attached systems. So some groundbreaking work. I've been doing permitting stuff for about permitting guidelines for about 16 years now, and so every time I do a new permitting guideline, I get bored. So I'm looking for new things, new challenges to address, and certainly the sheathing attached world we'll talk about in some detail and why that's becoming important. The vast majority of systems that are installed today, of those million rooftop systems, almost all of those million rooftop systems are member attached systems where we're actually lagging screws directly into roofing members like rafters or trusses. However, there's a whole new area that's been around for some time, but the structural horsepower behind it is really fairly recent. So we'll get into that. For wind exposure and design wind speed, we're talking about a wind exposure of B or C with a design wind speed not to exceed 150 miles per hour. So that's going to cover the vast majority of your regions. With there may be some Outer Banks areas that might not be covered by that in the Outer Banks of Virginia or Maryland, but it should be pretty close, 150 miles per hour. We're actually doing some tweaking to take it up to 180 miles per hour so we can deal with southern Florida. I just did a presentation for West Palm Beach a week before the hurricane hit, so it's very poignant, and we're working on stuff with that community. The week before, I was in Gulfport, Mississippi, and Hurricane Harvey hit the following week, so I would expect that here there should be a hurricane another week or so. Should be right around now. So start watching the weather. It just seems to happen.
Question. So when you talk about 150 miles per hour, is it for what period of time? 3 minutes, 5 minutes?
No, this is 3-second gust. This is the criteria that the current code uses. Yeah. So so the code has been using a couple of different wind speed criteria and has made a fairly large transition over the last couple code cycles to this 3-second gust criteria, which basically took the wind speeds to a much higher number than they were before. Okay, so let's dive into this. We'll talk about the structural requirements, continue. So wind exposure D, so we talked about B and C and D. For those of you who are not familiar with wind exposure levels, exposure D is waterfront property. Now, we have a fair amount of waterfront property in Chesapeake Bay, and God love them, they've got a waterfront property, they're going to hire an engineer. If they're facing a body of water that's more than a mile across. Now, my grandparents lived on the Wyeast River, and it was about 1/4 of a mile across, so that would not be exposure D. Okay, they were in exposure C. Okay, they were in the middle of the field, and they actually, trees everywhere. They had actually planted trees in the 1950s. They lived in Long Island, and every weekend they would drive down from Long Island and plant a few trees. And then, so by the time I came along, there's a forest at their house, and that was really cool. But so wind exposure D is fully exposed to a 1 mile or greater body of water, which means you're right on the Chesapeake Bay or on a very large bay, or the ocean. Exposure C is out in the middle of a field without anything really breaking the wind, and exposure B would be what we call suburban environment, or lots of trees around you, things like that, where that essentially you're getting wind breaks from neighboring structures and trees. The structure is also not on a hill steeper than 5%, where topographic effects can significantly increase wind speeds. And so certainly Maryland, Virginia, we can have those locations where somebody has a nice hilltop site, and that can be a fairly exposed location as well. And so these are all things that are in the building code that we're going to say, hey, we're going to solve 90% of the issues, and there's a few sites that we're not going to cover, and those folks are going to get covered by engineering. And that's okay. Ground snow load is not to exceed 60 pounds per square foot. That's well above anything we're going to see in this region. We have to go really far north to get above 60 pounds per square foot. Distributed weight of PV or less than 4 pounds per square foot. Typical PV systems are around about 2.5 pounds per square foot, all in. Some systems with glass-on-glass construction might be 3 pounds per square foot. So it's well within that distributed weight of the array. Building code has been lots of things added to the building code over the last couple of code cycles. One of which is acknowledgement that when we put a PV system on a rooftop of a house and cover that rooftop, the area that it covers really no longer has a live load requirement in it anymore, and the code will give us some credit for the fact that we can exchange a little bit of the live load for dead load. Now, engineers have been doing this for years, literally decades, but now it's actually in the code specifically. Okay, so let's talk about the roof. We're talking about 1 and 2 family structure or similar, and then that it's a permitted structure. So we have homes in our communities that predate any kind of building codes or permitting or anything like that. And certainly most of our historic districts and things like that are buildings that were built before there was a building code. That doesn't mean they're substandard construction, okay? It just means that they weren't part of a structural review. Sometimes that structure may look like fairly normal, typical construction with 16-inch on center or 24-inch on center rafters or trusses, and sometimes it could be very different. It's often full dimension lumber, all kinds of things like that, and so if it's not something that we can show compliance from residential span tables, then we may need some more information. So older homes might be challenging on that. If it's a newer home but we don't have documentation, maybe it was annexed into a community or something like that, then we can look at the span tables to see if it's typical normal construction that we're used to in our communities. So that's the idea of that permitted structure. We start with a permitted structure. We know that the building's been built for the environment that it's in, and then as long as we attach to that structure correctly, then everything's good. So the roof is framed with wood rafters or trusses no greater than 48 inches on center, and the framing members run upslope, downslope rather than horizontal purlins. And then the next one is a very important one, that the roof is structurally sound without signs of alteration, significant structural deterioration, or sagging. Now, some communities said, well, I want an engineer to verify that and say, okay, you know, we've had an engineer come in through and check through the entire structure and it's structurally sound. It's like, okay, well, I understand the desire to, you know, to have that on an engineer, but that's something that a contractor can certainly look at and review. And we're looking for things like members that have been cut, damaged by water damage, things like that, where they have to be repaired. An example of this might be somebody was looking for some extra attic storage space, right? So Christmas happens, you buy a bunch of Christmas lights to compete with your neighbors. They're LEDs now, so they don't use a lot of electricity. And so now you've got all this Christmas gear, and you got to find a place for it. And you go, okay, well, I'm going to put it up in my attic. You get up in the attic, and there's all this wood everywhere. And you're like, one of the things you got for Christmas was a chainsaw. And you don't have any trees in your yard, so what do you use your chainsaw for? Well, you make some room. So that would be structural alteration. And that would not be acceptable. So those little pieces of wood are there for a reason, and so yeah, so that would be one example of an alteration. Sheathing, 7/16 or thicker plywood or oriented strand board. Certainly the building code has required this for decades. So again, if it's a house that's been built in reasonable recent history, very rare to run across 3/8 plywood. And when you do, it's pretty darn evident from the ground. Usually you see waviness and things like that in the structure. If it's composition roof shingle, we're looking for a roof that has just a single overlay of shingles. For a variety of reasons, it's easy to seal that roof. However, if we did have 2 layers of shingles, which the code allows for, then we want to check the span tables and make sure we're good on the weight, dead weight, things like that. Mean roof height is not greater than 40 feet for member attached or 30 feet for sheathing attached. These are all assumptions that have been rolled into all the computer analysis that's been done on this to show compliance with the building code. Okay, so a 40-foot mean roof height of a house is exceedingly tall. That means that the peak of that ridge is going to be somewhere around 45 feet or more, and that is a really tall residence, particularly in the 1 or 2 family range. 30 feet is still extremely high. In fact, I'm not aware of any subdivision where the mean roof height of a house is greater than 30 feet. I've never seen one. Because again, you're talking about 35 feet tall house in a subdivision. That's really tall. In areas of significant seismic activity, then we want to make sure the array covers no greater than half the total area of the roof. This has to do with the mass of the roof and the mass of the building, related to building code requirements and things like that. It's not as big of an issue here as it is obviously in California, and half the total roof area is very, very conservative. We're probably going to end up pushing those numbers to at least 2/3, maybe up to 3/4, because the weight of these systems are pretty light.
So in such cases, just like the building loads are there for different zones in the building load mapping. Right. Some point of time we have same coverage of the roof may be different for different areas in the country. Less on this side and more on the we are not so prone to seismic activity.
Right. Yeah, so the idea is that if you don't have seismic concerns, then coverage on the roof is less of an issue. You still have to worry about the wind loading issues for sure, but you could go up to 70% or maybe 80%, and it's the mass of the roof isn't affecting any of the structural issues involved here.
Are you assuming this should be a slope roof?
Yes. In general, it's a sloped roof. I mean, when we get into sheathing attached, it doesn't apply to anything less than 2 and 12. Although we could have a member attached system that's in a flat roof. So we do have, there's a fair amount of residential that's flat roof, and particularly in urban areas. We have a lot of flat roof construction. If we want to go up in the air with those systems because we have kind of a roof deck or something like that, that's a completely different ballgame, and we're not trying to solve that issue at all. You know, if we're talking about staying within 10 inches of the roof. So on a flat roof, we're staying within 10 inches of the roof. All these things apply. Okay, so mounting equipment information. Now we get into the details from the supplier. And as I mentioned before, the mounting equipment has become a much bigger part of the story. And the reason it's become a bigger part of the story is because of UL 2703. So that's a new standard that's been developed over the last couple of years and is specifically for the mounting structure. And it covers, initially, its first purpose was to cover grounding and bonding on the electrical side. And so we have quite a few systems that have addressed grounding and bonding to bond the modules to the frames, to the racks, and use a single lug to actually take the entire grounded metal surface off to the equipment grounding conductor, and that's wonderful. It also now covers fire ratings of the system. And so the building code is now requiring fire ratings on the system, and so we have many systems that now have fire ratings on them. In California, about half the state requires Class A roofing for residential. That's very unique in the United States. General requirement across the country is Class C. And so most products are already Class C. However, as the building code and the fire code become more strict, we're going to see folks moving more and more toward Class A requirements because it makes a big difference. Now, apparently it didn't make a lot of difference when you have a firestorm, because those houses all had Class A roofs on them and they all burned to the ground. But that's not because of the fire. That's just the intensity of the fire. So then the last one is the specifying the anchor to roof sealing method. We have a lot of flashing products that are on the market. However, we also may be using sealants that are compatible with roofing, things like that, so that would be called out here. So let's talk about member attached systems. Oh, over here.
A quick question. You may be going to address it later, but last winter we noticed a lot of ice issues. That you've got an asphalt shingle roof, ice isn't usually an issue. It melts slowly, doesn't cause any damage to the house. With PV solar, we're seeing it slide off of the PV panels, ripping gutters off, ripping soffits off, damaging the roof. Is there anything that addresses that you're aware of? Because I can't find anything. We've had some significant damages because of
Right. And from your perspective, it's being made worse by the PV system? Because I know we have, and we every winter you're going to have gutters and fascia ripped off with icing situations. You know, there's obviously parts of the country where they do put in specific treatments to prevent those things from happening. But as far as anything specific in the code, I'm not aware of anything that's required.
where it's really hitting the homeowners is their homeowner policy says, hey, we don't cover PV solar, so it damaged your roof, all that ice slid off the panel, so we're not going to cover that damage either.
That's interesting because, yeah. I mean, whether that's true or not is another thing. I mean, you know, we don't have anything in our policy that specifically says anything about solar. Well, the way you fix that is when, you know, what I did when I installed the system on my house is I had it included in my homeowner's policy. So it's specifically in there. So if it did have an effect, they can't claim that it, you know, it's not part of the house or something like that. So that's one way to address that, is to specifically have it called out. But as far as, you know, whether or not a system makes things worse or better, I mean, that's the other thing, is there a way to build it in such a way? I don't know. I'm sure we could play around with that. In fact, I mean, if the array actually went over the edge of the gutter or right up to the edge of the gutter, then you may even go directly off of it, so it doesn't even get to the gutter. But But ice and snow are big issues. They're very problematic in a variety of places in a PV array, including the wiring. So that's one of the reasons why we encourage, keeping all the cables tied up neatly up underneath with clips and things like that, because if they're hanging down, they're going to get caught with snow and ice that travels underneath the array, and could potentially rip wires loose and things like that. So those are definitely things that have been looked at over the years, and there's also there's screening products that prevent squirrels from getting underneath arrays and things like that. Some of those products also may be designed for fire protection. So we have these fire ratings and things like that, and those may help prevent flow of material underneath the roof, underneath the panels. So we're not saying that we have everything figured out, and that part of this is, some of this is learning experiences, and certainly Virginia, Maryland, and Pennsylvania probably have some of the worst icing problems in the United States. And so as you get into higher latitudes, we're much more snow and things like that. Okay, so from a structural point of view and wind loading point of view, the first item we have on here is keeping the array back from the edge of the roof by at least twice the gap under the modules. So we're going to say the gap under the modules on number 3 is no greater than 10 inches. That's to the bottom frame of the module. And that's pretty high. 10 inches would be really high. Typical height off a roof is anywhere between 4 and 6 inches for a member attached system. This issue of twice the gap, so if you had a 6-inch gap underneath the modules, then you want to be a foot back from the edge of the roof. And this has to do with vortexes that happen right on the edge of an array. Now, one of the things that may relate to that snow and ice thing is that the main concerns are going to be at the ridge and the sides of the roof. And so the way the building code is moving, it's really not telling us whether it's the sides of the ridge. It would also apply to the eave of the roof. And maybe we'd want to modify that and say, well, that's not as big of a concern at the eave of the roof, but that's the way it's designed right now. These are things that have been learned from the solar world, is that there's this high pressure area, and we want to stay away from that because it puts too much loading on our perimeter anchors. The array doesn't cantilever over the perimeter anchors more than 19 inches. That's the second item there, and that's related to the 60 pounds per square foot. So it also addresses uplift forces on the panels. And so if we look at a typical PV system, and I'll just kind of bring up one of the designs here so we can kind of look at it. Let's take a look at this guy. So if you look at this here, these little black dots are anchors. And so between here and the edge of the panel would be the cantilever. And so the maximum cantilever we set up is about half a module. So we're not going to allow cantilever greater than half a module. And these perimeter anchors are the ones that get the most loading in all cases. So they get the most loading because they're going to be carrying the most weight if there's snow on top of them, and they're also carrying the most uplift force. And they're also in the most exposed location. They're on the edge of the array. So all those things, it's the perimeter anchors that basically control all the engineering related to these systems. I've actually seen, this is not to say it's a recommendation, I've actually seen a system on a commercial rooftop where the perimeter was held down with clips, and the center of the array had no clips on it at all. It was just laying there. Just laying there. And it had been there for 10 years. Been through lots of windstorms. And it was still sitting there. And that's because the wind loading in the middle of the array is fairly light. It's the wind loading around the perimeter that really is what we have to focus on when we're doing our layouts. So anyway, that's the cantilever issue there. So That's that 19 inches gap under the modules, no more than 10 inches, and then gaps between modules. So the building code, the new 2018 building code is going to specify that they want to see a 1/4 inch gap around every module, or a 1/2 inch gap on the long side if we don't have any gap on the short side. So most modules are rectangular in shape. And so this is a rectangular module here. We're saying that the gaps here would have to be either 1/4 inch all the way around or a 1/2 inch here, or if we had no gap on the short side, then we'd have a 1/2 inch on the long side. Does that make sense?
What's the purpose of this gap?
What's the purpose of that? What do you think? This has to do with wind loading. Why would a gap around the modules make a difference? Pressure relief. Exactly right. So the more you tie everything together, the more it becomes a kite or a sail. And it doesn't mean it can't be done. It's just saying, for the purposes of this engineering process, this gap makes a big difference for us in loading on the roof. Okay, there are products out there. In fact, Tesla is one of them that makes a product that where they butt the panels very closely to one another, and so then they have the engineering to back it up. Okay, fine. So we're not trying to solve the problems for one specific company. They have engineering. They supply that engineering with their drawings. That's fine. We're saying that if any Tom, Dick, and Harry comes down the road and mounts panels on the roof, we want to see a gap around. It's also very recent in the whole structural world. Okay. No. Yeah, so 99.9% of everything Tesla's installed is Solar City and frame modules using ZEP Solar. ZEP Solar is a mounting system, and ZEP can actually, you can put gaps in there, but it's generally they butt things close together. So they may end up having to start playing around with some of those things in their design in the future, depending on where they're at. And the higher the wind speed, the more they have to worry about it. Distance off the roof, the tighter you are, the less windage you have. And so it's a ratio between the gap and the height off the roof. And so again, we're coming up with a guideline that works anywhere in the United States. And so these are some basic rules. And obviously in a local area you could modify those if you have the engineering to back it up. Okay, so module rail orientation. Generally, we run our rails perpendicular to our rafters. So let's go back and look at that right there. So the rails here are actually running this way. Here's the rafters on 24-inch centers. The rails are running perpendicular to the rafters, and that's almost always how we do it. And that allows us to tie to basically every single rafter we'll see in a minute. However, if we're in a very low snow load area or no snow load area, whoops, then we could go parallel to the rafters. So does anybody know what the design snow load is in this area? 25 pounds per square foot in the city?
Yep.
30? Okay, here 40. Okay, so let's say 25 to 30. And so this is not going to be an option because that's relegated to 10 pounds per square foot, and that has to do with loading of rafters. Because if you run parallel to the rafters, you're going to load up individual rafters. You go perpendicular to rafters, you can actually alternate, as we're going to see here. We can alternate adjacent rows and stagger adjacent rows, so we're attaching to every single rafter on the roof, and we're completely distributed weight on the roof. Okay, so again, around here, we're just going to not worry about B. And then when we get to spacings on rafters and trusses, we're not going to exceed 4 feet between our anchors, and adjacent rows are going to be staggered, where trusses are 24 inches or less on center. So most of our trusses are going to be 24 or 16 inches on center. If we have 16 inch on center, we could go to every third rafter or every third truss, but then we're going to work our way, staggering our way down the roof so that we pick up every rafter or every truss. Okay, again, back to here. This is an example of a staggered pattern, and you're going to do some type of a stutter step, and normally we stutter step, we might stutter step on the top row here, and then we're going to go to every other rafter on every other row. And what that does, again, that does complete spreading of the load on that roof, so there's no point loading, things like that. And from a structural point of view, for a download on the roof, this is just the same, exactly the same as if we were to put an attachment to every single rafter on every single row. And that's a little counterintuitive to a lot of folks. What do you mean? That's, you know, that looks like half as good. No, it's just as good, and that has to do with how rafters are loaded and things like that. And so now there may be some instances, like when we go to 180 mile per hour wind regime, where we might end up putting anchors every single rafter, not because we're looking for downforce even loading. We're looking to provide enough uplift force that we don't rip the anchors off the roof. Because when we get up to 180 miles per hour, we're in a totally different world. Okay, and so we're more worried about ripping the thing off the roof than we are pushing down the roof. And so pushing down on the roof, this might be fine at 180 miles per hour, but it may not be enough. And we're doing the research on that right now to determine whether or not we need to go to more than this for 180 miles per hour. Does that make sense? Okay. Fun stuff. I know you guys. Now you want to become structural engineers, I know. These next two items here we're not going to talk about because this is for 10 pounds per square foot or no snow load. Again, those are going to be in the southern United States. Along the Gulf Coast maybe or close in southern, Mississippi, Alabama, those kind of areas where the lower parts of those states, no snow loads, Georgia, and then working your way across Arizona and then California. Okay, last things about member attached systems is that our upslope, downslope anchor spacing is going to follow the manufacturer's instructions. And so when we look at, going back to this example again, what determines the spacing this direction for our rails is not the rail manufacturer, but the module manufacturer. So the module manufacturer tells you how far apart and where to put the rails to attach to their module to prevent from overloading their module. So they're loading their module because they're designed for 50 pounds per square foot or 80 pounds per square foot snow loads. Okay, well those rails have to be in a very specific location because that's how they've been tested. So they might give you a range of where on that module you can actually put that rail. And so that's being constrained by the module manufacturer, not by the rail manufacturer. Okay, and then the anchor fastening, the standard anchor fastener that we're going to talk about is a 5/16 lag screw with 2.5 inch embedment in the structural member. So normally those lag screws are anywhere between 3.5 and 4 inches long because they have to go through all of the pieces, not just they might have some kind of a bracket that they're holding on to, and that bracket, then it goes through the bracket to the roofing material, which has no structural strength, goes through tar paper, all that mess, and then finally makes it to the decking and then into the member. So by the time you get there, you're talking about a fairly long lag screw to get 2.5 inch embedment into that member. Alternatively, a manufacturer, we've seen products out there where they might use 2 1/4 inch lag screws and show engineering basically shows that they're as good or better than a single 5/16 lag screw. Okay, so that's member attached, by far the most common method and what you're most likely to see. In the near future, however, there are several products on the market that have come along that are working with sheathing attached systems, And there's some real advantages to sheathing attached systems. At first blush, you go, wow, that doesn't seem all that safe to be able to just connect to the sheathing. How do you hold on to it and things like that? And we'll address some of those things. But the real benefit of sheathing attached is that it's far more forgiving for the installer. Okay, so if you have a well-designed sheathing attached system, you can install it more quickly. You don't have to worry about where rafters are. It's kind of like hanging pictures on a wall. If you had pictures that always had to hit a stud, that's a challenge, because now we got to have a stud finder, we got to find the thing, we got to get into it. But if we have an attachment where we can just put a hook in and hang the picture anywhere we want, we put it where we want it, not where the structural member necessarily is. And so that's kind of the sheathing attached method. We'll see that we have lots of stipulations on that. We still have that twice the gap under the modules. Typically, sheathing attached systems are lower to the roof, so they're lower profile, less than 5 inches off the roof, and so we're going to constrain them to 5 inches, no more than 5 inches off the roof. Again, the 19-inch cantilever for snow loading and wind loading around the perimeter. And then we're actually going to specify a larger gap than the code requires of 3/4 of an inch on the short and long sides of the module. And that's actually fairly common, because normally we see maybe a 1 to even 2 inches of gap on some of these systems. But again, that's for that pressure relief we talked about. And then we're also going to limit this to a roof slope that's at least 2 and 12 pitch. All right, the next slide or so, I'm going to summarize very quickly without going through all this material. In fact, since this is a lot of stuff, let's go ahead and take a break now. And when we come back from the break, we'll finish this up and then go on to the next section.